So we're in section, what are we at, 8.5. So the first thing I want to do is point out a distinction, kind of in how we a place where we have to be careful in how we count. So what we're doing is counting things that can get kind of tricky to count. So let's say, and when we talk about counting, when we talk about probability, the classic example is an urn that contains like ping pong balls. So let's say we have an urn with 6 balls, numbered 1 through 6. For this first example, we're going to pick one out, write down the number, put it back, pick another one out, and write down the number. So we're going to pick one, write the number, return it, and then we're going to pick another. We want to know how many ways we could get a total of 8. So this is the thing that we're counting in this particular example. How many ways can we get 8? So what are the combinations of the numbers 1 through 6 that are going to give us 8 that we could pick out of this? So we only have numbers 1 through 6. So our first one would be, let's start with the lowest number. We get a 2 and a pair. We could pick out a 2 and then a 6, right? We could pick out a 3 and then a 5. We could pick out a 4 and then a 4. Or we could pick out a 5 and then a 3, or a 6 and then a 2. And those are the ways that we could end up with a total of 8. So we have 5 ways. Now for the second example, we're going to say we have the same urn, the same 6 balls. This time we're going to pick one. We're going to write the number and then not return it. We're going to pick another without returning it. So without returning the first. So we could still pick a 2 and then a 6, right? We could still pick a 3 and then a 5. Could we pick a 4 and then a 4? No, because if we take the 4 out, it's not there to pick the second time. So we can't pick a 4 and a 4. That combination doesn't come up. But we could pick a 5 and then a 3, and then a 6 and then a 2. So this time there are only 4 ways. We call the first way, we call the first example with replacement. And the second example is without replacement. And when we count things, it's important to know, are we talking about with replacement or without replacement? Do we allow repeats? Here we're allowing a repeat. Here we're not allowing a repeat. Kind of the same idea. So how we count them depends on whether or not we have replacement, we have no replacement. We have repeats, we have no repeats. All right, so the first thing we want to talk about, we'll keep this in the back of our head. First thing we want to talk about is called the fundamental counting principle. And we all use this pretty much every day. To count kind of simple combinations of things. So let's say you have four shirts and 3 pairs of pants, and none of them clash. So how many different outfits could you make out of your 4 shirts and 3 pairs of pants? 12. And how do we get 12? We multiply. So the fundamental counting principle tells us if we have 2 events, so one of the events that we just talked about was our pants and one was our shirts. 2 events, one can occur m ways. And the other can occur n ways. Together they can occur m times n ways. So the fundamental counting principle says when we have things that can happen in different ways, find out how many ways they can happen together, we multiply. And this is true for any finite number of events. So if we have 3 events that all happen in different numbers of ways, we can multiply those 3 things together. So we go to the ice cream shop and we can get 3 flavors of ice cream and 2 kinds of sprinkles and 2 kinds of sauce. We'd say 3 times 2 times 2 is the total number of things we could get at the ice cream shop. So that's what the fundamental counting principle tells us. So let's look at an example of using the fundamental counting principle where we have to be careful with replacement or no replacement. So let's say we want the number of arrangements of 3 letters from the alphabet. So how many letters can we pick for the first letter in our arrangement from the alphabet? 26. And if we're allowing the letters to repeat, how many letters do we have to choose from for the second letter in our arrangement? 26. And if we allow repeats, how many do we have for our third letter? 26. So the number of arrangements, if we allow the letters to be repeated, is 26 times 26 times 26. What if we didn't allow repeats? So this would be a with no replacement example. So how many, if we're not allowing repeats, how many do we have for the first letter? 26. For the second? 25. And then 24. So our numbers, total would be slightly different with repeats and without repeats. We could do the same kind of example with like a license plate. Say we had a license plate with 3 letters and 3 digits. If we allowed the letters to repeat, the first part of the license plate could have this many letters, and then our digits, we'd have our multiply the number, however many digits we have over here. If we allowed it to repeat, we'd have, how many digits would we have to pick from? We were picking for arrangements of digits. 10, 0 through 9. So we could have 10, and then if we didn't allow repeats, we'd have 10 times 9 times 8, etc. So this is just some couple easy examples of using the fundamental counting principle. So questions on that. Something that we use kind of intuitively when we're talking about combinations of things, arrangements of things. All right, the next thing that we want to talk about is what if we want to arrange a smaller number of objects selected from a larger set? And the first thing we're going to talk about that has to do with that is permutations. So we'll talk about a couple of examples first, and then we'll come up with a formula. Because what we want to do is not have to count each of these individually. We want to come up with a process for counting them. So let's talk about how many ways we can arrange 4 letters We're going to arrange the letters A, B, C, D. And once we use one, then it's not available to be used again. So we have, basically we're filling 4 slots with these letters. So how many choices do we have for the first slot? How many letters can go in the first slot? 4. And then once we've used one of the letters, how many do we have left to go in the second slot? 3. And then how many do we have left? 2. And then 1. What is 4 times 3 times 2 times 1? 4 factorial. So we could arrange these 4 letters in 4 factorial different ways. And 4 factorial is 24. Now let's say we want to arrange these 2 at a time. So we're only picking 2 out of the 4. So we arrange 2 letters from A, B, C, D. So how many do we have? How many can go in the first slot? 4. And how many choices do we have to go in the second slot? 3. And we're just arranging those two letters. So we're just picking 2. So we get 12. So if we're only picking 2 out of those 4, we get 12. So what we want is a way to come up with a formula that would let us talk about any arrangement of a smaller set from a bigger set. And what we call that is a permutation. And the way we calculate that is our formula. And we write NPR for permutation, and it is n factorial over n minus r factorial. So for this example, we had 4 factorial divided by 2 factorial. That's where we got the 12. And the other way we can calculate this is we get n times n minus 1 times n minus 2 times dot dot dot, and we do this for our numbers. And a permutation is an arrangement of a smaller set from a larger set where order matters. And when we say order matters, we mean that a different arrangement of those things turns it into a different thing. So a different arrangement of A, B, C, D is a different arrangement. So a couple of the key words that you'll see when you're talking about permutations is you'll talk about how many ways can someone come in first, second, and third. So a different order of first, second, and third makes it a different finish for the race. Committees come up a lot with permutations. A committee with a president, a vice president, and a secretary. So you're filling those specific slots. That would tell you that you're talking about a permutation, because a different person being president, vice president, and secretary makes it a different thing. So that's what we mean by order matters. So we're talking about a committee of 4 out of our classroom of 30. We would, where we're looking for a president, a vice president, and a secretary, that would be a permutation, because we're filling those 3 specific slots. And we calculate our permutations using this formula. And what we're doing here is we're taking all the ways that all of these could be arranged together, and then we're dividing by the number of ways that the smaller subset can be arranged among themselves. That's where this formula comes from. So questions on our formula there? So let's do a quick calculation. So if we had the example that I used, a committee, we want a president, a vice president, and a secretary. So president, vice president, and secretary picked from a class of 30. That would be 30 P3. So we want to figure out how many arrangements of 3 things out of those 30 that we have. So that would be 30 factorial over 30 minus 3, which is 27 factorial. And that would be 30 times 29 times 28. And I said we multiply 3 numbers. That's what I meant by R numbers. And I multiply this out, and that would tell me how many officers, arrangements of officers, of president, vice president, and secretary I could have from a class of 30 people. That would be an example of a permutation. All right, questions there? All right, so sometimes we have repeated things in our set. So say we are arranging some letters, and we had more than one A and more than one N and more than one T, for example. Well, then our formula has to change a little bit. When we talk about those, we have another formula. So our permutation formula changes a little bit because we can't tell the 2 things that are the same, we can't tell them apart. So a different arrangement of those 2 things doesn't make a different arrangement of our set. So we need to talk about distinguishable permutations. And distinguishable permutations come up when we have repeated items in our set. So let's say our set has n objects, and we have n1 of one kind, n2 of another kind, n3 of a third, etc. The number of distinguishable permutations is we have n factorial on the top, just like before, and that's how many ways we can arrange, how many different ways we can arrange all n of those things. And we're going to divide by n1 factorial times n2 factorial times n3 factorial, dot, 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 until we've taken care of all of the things, all of the elements in our set. And again, what we're doing is we're dividing by the number of different ways that we could arrange those things that don't make the arrangement different. So let's look at an example of calculating a distinguishable permutation. So let's say we want to arrange, we want the number of distinguishable ways we can arrange mathematics, the letters in the words mathematics. So I look at this and I say we have a total of 11 letters. So n equals 11, but I have two m's, I have two a's, and I have two t's. So I can't distinguish between those two a's and those two m's and those two t's. So that's why I end up having to divide by these extra terms here. So my distinguishable arrangements are going to be 11 factorial. That's a total number of ways that I could arrange those 11 letters. And then I'm going to divide by 2 factorial for the m's, 2 factorial for the a's, 2 factorial for the t's, and the rest there's just one of those. So I'd end up with a 1 factorial, 1 factorial, 1 factorial, so I don't have to worry about those, because 1 factorial is just 1. So my number of distinguishable arrangements would be 11 factorial over 2 factorial times 2 factorial times 2 factorial. And the 2 factorials take into account that we can arrange these two m's in 2 factorial ways, these two a's in 2 factorial ways, and these two t's in 2 factorial ways. And when I calculate this out, this comes out to 4,989,600. 4,989,600 different arrangements of those 11 letters. Questions there? So the distinguishable permutations come up when we have repeated elements in our set. And dividing by these 2 factorials takes into account the number of ways we could arrange those that don't make it different. All right. Last thing we need to talk about is combinations. Combinations are similar to permutations in that we have our items, pick from a set of n items, but the order does not matter. So an example of a combination, and we'll write down the formula here in just a second. An example of a combination would be, rather than a president, a vice president, and a secretary, it would be just a committee of 3 people. So if I change the order of those 3 people on the committee, it doesn't make it a different committee. It's still the same committee. If we're talking about a different kind of sandwich, a BLT is the same as a as an LBT. So changing the order of the ingredients on the sandwich doesn't make it a different sandwich. Now some people might argue that one, that a BLT is different than an LBT. You have to put it in the right order for it to be the right kind of sandwich. For me, the mustard has to go on the bread. You can't put the mustard on the other part. It has to go on the bread. So that would be an example of a combination, where a different arrangement of the things doesn't turn it into a different thing. So some people would argue that a sundae with strawberries and chocolate sauce is the same as a sundae with chocolate sauce and then strawberries. So that's kind of a subjective thing. But our formula for combinations is NCR, and this should look familiar. N factorial over R factorial times N minus R factorial. And where have we seen this before? Do you remember? This is the same as the binomial coefficients. So what we're doing here with our combination, our formula for combinations, if we go back to our formula for permutations, so we're dividing, the only difference between those two is the R factorial in the bottom. So what we're doing for the combinations is we're dividing the number of arrangements of the n things by the number of arrangements of the n minus R things, and then we're dividing out the number of arrangements that for the R things that don't make it into a different combination, because we can order those things differently and it's still the same thing. So we divide by those arrangements of the different pieces that don't make it different. That's where our formula is coming from. So let's do our example. Let's do a committee of 3. From a class of 30, rather than a president, a vice president, and a secretary. That would be a combination. We're just talking about a committee. A different arrangement of the people doesn't make it a different committee. So we're talking about 30C3, 30 factorial over 3 factorial times 27 factorial. And we decided this is going to be 30 times 29 times 28 divided by 3 times 2 times 1. So let's see, how can we simplify this? We'll do this by hand. That'll give me a 10, divide this by 2, and that'll give me a 14. So I get 10 times 29 times 14. And whatever that comes out to would be our number of combinations, our number of committees that we can form, committees of 3 people formed from a class of 30. So a little bit less than our number of president, vice president, and secretary. Questions there? So these formulas just give us a way for counting things that can be difficult to count otherwise. And what we're going to do with these permutations and combinations is on block day we'll use them to calculate probabilities. So we'll have to count the things to calculate probabilities. All right. Homework. There we go.